In the early 1900s, physicists were making groundbreaking discoveries in the secrets of the atom. However, they often made observations that they couldn't explain using the known physics at the time. Albert Einstein won the Nobel Prize in Physics in 1922 for his explanation of the photoelectric effect. The photoelectric effect is the phenomenon whereby electrons, now called photoelectrons, are ejected from the surface of a metal when light shines on its surface. Before Einstein, physics knowledge couldn't explain what we are about to learn. In fact, it predicted the opposite of what actually occurred. The original scientists studying the photoelectric effect reasoned that the intensity of light shining on a metallic surface should be the main factor that determines the kinetic energy of the photoelectrons emitted. The data from their experiments didn't show this to be true, though. Kinetic energy is the product of 1/2 the mass in kilograms of an object and its velocity in meters per second squared. All electrons have the same mass, so the varying kinetic energy means that the photoelectrons' velocities are different. Another counterintuitive observation noted that it didn't take an extended period of time for the photoelectrons to leave the surface of the metal once the light was incident to its surface. Let's make an analogy to this using water. Water in a pot on a hot stove doesn't evaporate the instant it comes in contact with the thermal heat. Electrons, though, are instantaneously ejected from the metal surface when light is shown upon it. Think how strange it would be if the water in our pot did instantly evaporate when it was exposed to heat. This analogy gives us a taste of how different the quantum world, or the subatomic level, is compared to the macroscopic world we observe every day. Let's take a dive into the quantum world and learn some details about the photoelectric effect. White light is made up of a spectrum of colors, ranging from red with the lowest frequencies to violet with the highest frequencies. You may remember learning the acronym ROY-G-BIV, which stands for red, orange, yellow, green, blue, indigo, and violet. Physicists shined these colored lights on various metallic surfaces and made observations. Starting with red light on one particular metal, they observed that no electrons were ejected from the metallic surface. Thinking that to be pretty strange, they increased the intensity of the light, and nothing changed. No photoelectrons were emitted. Next, they shined green light on the same metal, and noticed that photoelectrons were emitted with a specific kinetic energy. Shining violet light resulted in the same quantity of photoelectrons ejected as with the green light, but with higher kinetic energies. Finally, they increased the intensities of the green and violet lights. This caused more photoelectrons to be emitted, but their kinetic energies were the same as they were with the less intense light. To conclude, the higher the frequency of light, the higher kinetic energies of photoelectrons emitted, and the higher intensity of the light, the higher quantity of photoelectrons emitted. The other factor in the photoelectric effect is the material the light shines on. Materials have a minimum frequency that will strip electrons from them, called the threshold frequency. The work function of a material is the minimum light energy required to eject photoelectrons. In other words, to remove an electron from the metal surface, a certain amount of energy is needed. Therefore, the frequency of the light has to be high enough to give that electron enough energy to overcome the work function. Any frequency of light below the threshold frequency results in no photoelectric effect, and the intensity of the light won't change this. Any frequency above the threshold frequency will eject photoelectrons, and the higher the frequency of light, the higher the kinetic energy of the photoelectrons. The photoelectric equation relates the frequency of light shined on a specific material, the work function of that material, and the kinetic energy of the photoelectrons emitted. It's read as HF equals phi plus E sub k, in which H is Planck's constant, which is 6.63 times 10 to the minus 34 joule seconds. F is the frequency of light in hertz. Phi is the work function of the material in joules. E sub k is the maximum kinetic energy of the photoelectrons. You can see that the energy of a photon of light is HF. If the light doesn't have a big enough frequency, or F, no photoelectrons will be emitted. The photoelectric effect is the phenomenon whereby certain frequencies of light shined on metal results in photoelectrons emitted from the surface with a specific kinetic energy. The frequency of light determines whether photoelectrons are emitted, and the higher the frequency, the higher the kinetic energy, which is the product of 1/2 the mass of an object and its velocity squared. The material itself also determines whether photoelectrons are emitted. The intensity of light affects the quantity of photoelectrons emitted, but kinetic energy does not change. The minimum frequency of light for emitting photoelectrons is the threshold frequency of the metal. The work function of a material is the minimum light energy required to eject photoelectrons.